Good afternoon, my dear students. My name is Gaurav Singh. I am an assistant professor in St. Peter's Engineering College at Department of Science and Humanities. I have been teaching chemistry to B.Tech first year students. Today, we are going to discuss Unit 2, that is second unit, water and its treatment. The today's topics are introduction, sources of water, impurities of water, okay, uses of water. Then we'll discuss hard water. In that, we'll discuss types of hardness, degree of hardness, units of hardness, determination of hardness of water, potable water and its specifications, and treatment of water for municipal supply. Okay, so these are the topics which we are going to discuss today. So let's begin. Water. Water is a natural gift on earth, as we know. Without water, we cannot survive. It is essential for humans as well as animals and plants. Human beings use water for drinking purpose, cooking, bathing, cleaning, and washing. Water is found in three physical states, as we know: liquid, solid, and gases. The freezing point of water is 0 degrees Celsius and the boiling point is 100 degrees Celsius. We are aware of. Several special behaviors found in water are due to the hydrogen bond present in it. In nature, water is present in abundance. There is huge water, but about 96% of water forms the oceans. About 96 or more than 96% of water is present in oceans. 2.2% forms the ice and snow. 1.2% forms the groundwater, and only 0.003% of water is useful for human consumption. Only 0.003% of water is useful for human consumption. It is therefore essential to use available water carefully and economically. The rest forms the surface water and the water present in the atmosphere. The various sources of water are rivers, tanks, reservoirs, sea, oceans, wells, tube wells, rain, glaciers, streams, lakes, etc. Okay. Now we come to the term hardness of water. What is the hardness of water? Okay. Water is a very good solvent, as we know, and even called as the universal solvent. Most of the inorganic salts are soluble in water. The water that has calcium and magnesium salts dissolved in it causes hardness of water. So what causes the hardness of water? The calcium and magnesium salts which are dissolved in water. The calcium and magnesium salts dissolved in water. These salts, they cause hardness of water. Water passes through rocks and flows on the ground. The calcium and magnesium salts that are present in the rocks are dissolved in water and make it hard. Hard water does not give leather. Remember this. Hard water does not give leather with soap, while soft water easily gives leather with soap. Remember this term. Hard water does not give leather with soap, while soft water easily gives leather with soap. Hence, the hardness of water is its characteristic which resists the lathering with soap. So what it does, it resists, it is its characteristic which resists the lathering with soap. Chemically, it can be understood as follows. A soap is a sodium salt, we can see here. A soap is a sodium salt of higher fatty acid, such as stearic acid, C17H35COOH, stearic acid. Soap, in the absence of calcium or magnesium ions, give lather with water easily. But in the presence of calcium and magnesium ions, it reacts with them and forms insoluble soap that appears as precipitate or formation of scum. See, insoluble scum is formed in presence of calcium and magnesium ions if they are present in the water. Okay. Now, what are the disadvantages of hard water? What are the disadvantages of using hard water? As far as domestic use is concerned, during washing, when hard water is used for washing purposes, it does not produce lather freely with soap. Rather, it produces sticky precipitates of calcium and magnesium soaps. The precipitation continues to take place till all calcium and magnesium salts in water are precipitated. After that, the soap gives lather with water. As a result, wastage of soap takes place, and in the presence of iron salts, it may cause staining of cloth also. Staining of cloth. Second, bathing. Hard water forms sticky precipitate with soap on bathtub and body. Thus, cleaning quality of soap is reduced and a lot of it is wasted. Cooking. Due to the presence of dissolved hardness producing salts, the boiling point of water is elevated. It is elevated. Hence, more fuel and time are required for cooking. More fuel and time are required for cooking. The dissolved salts are deposited as carbonates on the inner walls of the utensils. Drinking. Hard water causes bad effect on our health. Calcium forms oxalate crystals in urinary tracts. In industrial use, textile industry, hard water produces precipitates of calcium and magnesium with soap. The fabrics, when dyed later on, do not produce exact shades of color. They do not produce exact shades of color. Iron and magnesium salts containing water produces colored spots on the fabric. Colored spots on the fabric. So it spoils the fabric. Okay. In sugar industry, water containing sulfates, nitrates, alkali carbonates, if used in sugar refinery, refining causes difficulties in the crystallization of sugar. Moreover, the sugar so produced may be deliquescent. Dyeing industry, the dissolved calcium, magnesium, and iron salts in hard water react with costly dyes, forming undesirable precipitates, which yield impure shades and give spots on the fabric being dyed. Laundry, hard water causes wastage of soap, iron salts cause coloration of clothes. Coloration of clothes. Pharmaceutical industry, hard water, if used for the preparation of pharmaceutical products such as drugs, injections, ointments, may produce undesirable products in them. Paper industry, iron salts affect the color of the paper. Affect the color of the paper. Now, types of hardness. Types of hardness. There are two types of hardness. The first one is temporary hardness. The second one is permanent hardness. First one is temporary hardness, and the second one is permanent hardness. First, second. This temporary hardness is also known as carbonate hardness. This is also known as carbonate hardness. Carbonate, carbonate, carbonate hardness. And this is known as non-carbonate hardness. Okay, non-carbonate hardness. So temporary hardness is due to the presence of bicarbonates of calcium and magnesium that can be removed by boiling. On boiling, the soluble calcium and magnesium is converted into insoluble carbonate that can be removed by filtration. So on boiling, the soluble calcium and magnesium bicarbonates, they are converted into insoluble carbonate that can be removed by filtration. See, calcium bicarbonate after boiling, it precipitates, it forms calcium carbonate. Similarly, magnesium bicarbonate after boiling, it forms magnesium hydroxide, so which are insoluble in water and they can be precipitated or they can be filtered and removed. Okay, so temporary hardness is due to the presence of bicarbonates of calcium and magnesium. Okay, now permanent hardness. Permanent hardness cannot be removed by boiling. Remember this fact. And it is due to the presence of calcium, chlorides and sulfates of calcium and magnesium. It is due to the presence of chlorides and sulfates of calcium and magnesium in water. These salts cannot be removed by boiling. Remember this. These salts cannot be removed by boiling. So if water contains calcium chloride, calcium sulfate, magnesium chloride, magnesium sulfate, the water is known to have permanent hardness. Remember this. Now, measurement of hardness or degree of hardness. Measurement of hardness or degree of hardness. The hardness of water is measured in terms of calcium carbonate. The hardness of water is measured in terms of calcium carbonate equivalents because it is highly insoluble in water. There are two factors why we use calcium carbonate as a reference to calculate degree of hardness, because it is highly insoluble in water. The first thing, first point, it is highly insoluble in water, and secondly, its molecular weight is 100. Secondly, its molecular weight is 100. That makes the calculation easier. That makes the calculation easier. Okay. So the degree of hardness or the hardness is calculated in terms of calcium carbonate equivalents. Calcium carbonate equivalents. Okay. Why do we use calcium carbonate as a reference material to calculate hardness? Because it is highly insoluble in water, and secondly, its molecular weight is exactly 100. That makes the calculation easier for us. Okay. Now, Units of hardness. Units of hardness. We in our syllabus we have four types of units of hardness, and we are going to discuss only these four types: parts per million, milligram per liter, degree Clark and degree French. Degree Clark and degree French. Right? Degree Clark and degree French. Okay. So these four type units are generally used as units of hardness to express units of hardness. Okay. Parts per million, milligram per liter, degree Clark, and degree French. Now, parts per million or ppm. Parts per million or ppm. It is the number of parts of equivalent calcium carbonate per 100 per 10 to the power 6 parts of water. This is 10 to the power 6 parts of water. So what is parts per million? It is the number of parts of calcium carbonate equivalent per 10 to the power 6 parts of water. For example, 50 ppm hardness means 10 to the power 6 parts of water has 50 parts of equivalent calcium carbonate. 50 parts of equivalent calcium carbonate. So remember in easy term, it is the number of parts of calcium carbonate. It is the number of parts of equivalent calcium carbonate per 10 to the power 6 parts of water. 10 to the power 6 parts of water. Okay. Remember this. Now, next one, milligram per liter. Milligram per liter. It is the number of milligrams of equivalent calcium carbonate. It is the number of milligrams of, it is the number of milligrams of equivalent calcium carbonate per liter of water. Per liter of water. Remember this. Per liter of water. Okay. 1 milligram per liter hardness means 1 milligram of equivalent calcium carbonate per liter of hard water. Per liter of hard water. 1 kilogram of water is equal to 10 to the power 6 parts. 10 to the power 6 parts. 10 to the power 6 parts. Okay. So 1 ppm will be equal to 1 milligram per liter. Remember this. 1 ppm will be equal to 1 milligram per liter. Next, degree Clark. Degree Clark. It is the number of grams of calcium carbonate per gallon of water. It is the number of grams of calcium carbonate per gallon of water, such as the number of parts of calcium carbonate equivalent hardness. Remember this one. The number of parts of calcium carbonate equivalent hardness per 70,000 parts of water. Per 70,000 parts of water. Per 70,000 parts of water. Degree French. It is the number of parts of calcium carbonate per 10 to the power 5 parts of hard water. It's 10 to the power 5. 10 to the power 5 parts of hard water. Okay. Hardness, 1 degree French means 1 part of calcium carbonate equivalent per 10 to the power 5 parts of hard water. 10 to the power 5 parts of hard water. 10 to the power 5 parts of hard water. Okay. Now, what is the relationship between these units? Remember this. 1 ppm is equal to 1 milligram per liter, which is equal to 0.1 degree French, 0.1 degree French, and which is equal to 0.07 degree Clark. Remember this relationship. 1 ppm is equal to 1 ppm equals 1 milligram per liter equals 0.1 degree French equals 0.07 degree Clark. This is the relationship which may be asked in examination. And this is also important as far as examination is concerned, units of hardness. Okay. The definition you should remember. Now, Very important point, very important topic we are going to discuss. Estimation of hardness of water by complexometric method, which is also known as EDTA method, which is also known as EDTA method. Estimation of hardness of water by complexometric method. Okay. This is also known as EDTA method. What do we do in this? See, okay. So in this EDTA method, the hard water sample, we take hard water sample and we add EBT indicator. After that, we add buffer solution, okay, in a conical flask, and then it is titrated against standard EDTA solution, standard EDTA solution, and the endpoint is this blue color. The endpoint is this blue color. This is the structure of EDTA. This is the structure of EDTA, and this is the structure of EDTA with the metal complex. The complex which EDTA forms with the metal or the metal ion. Okay, and this is the structure of EBT indicator. What is EBT indicator? Areochrome black tea. EBT indicator is areochrome black tea. Areochrome black tea. EDTA is ethylene diamine tetraacetic acid. Ethylene diamine tetraacetic acid. Okay, ethylene diamine tetraacetic. Now, the principle behind estimation of hardness of water by complexometric method, as we have discussed recently in the last slide, the structure of EDTA. This is the structure of EDTA when it forms complex with the metal ion. This is a free structure and this is the complex structure. Okay. So what happens? EDTA, ethylene diamine tetraacetic acid, forms colorless, it forms colorless stable complexes with calcium and magnesium ions present in water at pH around 10 pH. To maintain the pH of the solution as at 9 to 10, buffer solution, which is a mixture of ammonium chloride and ammonium hydroxide, is used, okay, to maintain this pH. Now, areochrome black tea is used as an indicator. The sample of hard water must be treated with buffer solution and EBT indicator, which forms unstable wine red colored complexes with calcium and magnesium ions present in water. So what happens? EDTA, it forms colorless stable complexes with calcium and magnesium ions, whereas areochrome black tea, it forms unstable colored complex. It forms unstable colored complex, or we can say wine red colored complex with calcium and magnesium ions present in water. Okay, you can see here, this is the structure of EDTA, ethylene diamine tetraacetic acid. If suppose we use this is a hard water sample, or in hard water sample we have calcium and magnesium ions present, hard water sample. When EBT is added in the hard water and around 3 to 4 ml of buffer solution is added, we get a wine red color complex which is unstable. We get a wine red colored complex which is unstable. Okay. In this, when EDTA, when it is, this solution is titrated against EDTA, so we know that EDTA forms stable complex with calcium and magnesium ions. So what happens? This EDTA, it replaces this, or we can say it displaces this EBT from this complex, and it forms EDTA calcium and magnesium complex, or EDTA metal complex is formed. which is colorless, but it is stable complex. It forms a stable complex, but colorless. And this EBT indicator is released in the solution, and it gives a blue color, which is a endpoint. It indicates the endpoint, the blue color. Actually, we get steel blue color after titration is over. Okay. So this is the principle behind complexometric titration. Now, the procedure, there are three steps. There are three steps which are followed in estimation of hardness of water by EDTA method. Okay. The first step is standardization of EDTA. The first step is standardization of EDTA. In this, 20 ml of standard hard water is taken into a conical flask. Here, this is the conical flask where 20 ml of standard hard water is pipetted out. Okay, and in this we add 3 to 4 ml of buffer solution, 5 ml buffer solution, and few drops of areochrome black tea indicator. The indicator, which is originally blue color, would acquire a wine red color. So a wine red color is formed after adding buffer solution and areochrome black tea. Then it is this solution is titrated against the standard EDTA solution present in the burette. This is the burette. Okay, so this titrate with EDTA solution taken in the burette till the wine red color changes to blue, which is the end point. Blue color is the end point. Okay, let the burette reading be EDTA. Let the burette reading of EDTA be V2 ml. Suppose this much EDTA is consumed, which we can term at V2 ml is consumed. Okay. Now the second step is determination of total hardness. The second step is determination of total hardness. Repeat the initial step is repeated as we had discussed in the last slide. Repeat the above titration method for sample hard water. But in this, the second time we use sample hard water. We do not use standard hard water. We use only sample hard water. It may be tap water or any other lake water or river water. So we use sample hard water instead of standard hard water. Okay. And the procedure is the same. The same procedure is followed. Okay. And suppose this time the EDTA consumed is V3 ml. This much V3 ml is consumed. Okay. Now we note down the reading, and the last step is determination of permanent hardness. Determination of permanent hardness. The last step in this, we take 100 ml of sample hard water, which was used in the second step, the same water. Take 100 ml of sample hard water in 200 ml beaker. Boil it to remove temporary hardness to about half of this volume and cool to room temperature. Filter through filter paper to remove insoluble calcium carbonate and magnesium carbonate. Then make up this volume to the original 100 ml by adding distilled water. Now pipette out 20 ml of this solution into a clean conical flask. Then repeat the process of titration steps as mentioned above. Now let the burette reading of EDTA be V4 ml. Now this time, suppose it is the volume consumed is V4 ml. Okay. Now we can do the calculation.